This module is about the t-test. We're going to talk about inferences about population means. When we're done, you should be able to answer the following questions. What's the main use of the t-test? How is the distribution of t related to the unit normal? When would we use a t-test instead of a z-test? Why might we prefer one to the other? What are the chief varieties or forms of the t-test? What's the standard error of the difference between means? What are the factors that influence its size? More questions. Identify the appropriate version of t. Identify the appropriate version of t Identify the appropriate version of t to use for a given design. Compute and interpret t-tests appropriately. Given that the null hypothesis is mu is 75, the alternative is not 75. Standard deviation of y is 14 and n is 49. And t is, with 05 and 48 degrees of freedom, is 2.01. Construct a rejection region. Draw a picture to illustrate. Okay, so by way of background, the t-test is used to test hypotheses about means, and two means, when the population variance is unknown, and that's the usual case. T-test is closely related to, the distribution of t is closely related to z, the unit normal. The t-test was developed by a guy named Gossett for quality control of beer. He's working for Guinness. The t-test comes in three varieties: the single sample, the independent samples, and the dependent samples t. So I'm going to show you examples of each of these. The single sample t, we only have one group, and we want to test that mean against a hypothetical mean or the status quo. So we might have an idea about the average GPA of students over the last so many years, and we might want to institute a training program and see if the GPA for those folks is better, or a selection program and see if the GPA for the selected folks is better. So we can do a single sample t where we have only one group. Then we have the independent samples t, which is the most common kind of t-test. We have two means, we have two groups, there is no relation between the groups. So for example, people are randomly assigned to the experimental group and the control group. That's the independent samples t. And then in the dependent t, or dependent samples t, we have two means. So again, either we have related people, the groups are related like husband and wife, left hand, right hand, or the same people are tested twice, so left hand, right hand, before and after, or pain-free and placebo, or something like that. So, and if it's before and after, we have to be very careful, otherwise we have that single group pre-post design. But I'll talk more about that later. Right now, three kinds of t. So before we do t, I'm going to show you the same thing in z. So we can test hypotheses about population means given sample data, sample means, using z. And if we have big samples, z and t turn out to be pretty much the same. So here we go. For single sample z, you've got the observed mean, x bar, and then you got the population mean mu, and you've got to compare that to the estimated standard error of the mean. Okay, so this is kind of a z-score, right? I mean, a z for the mean. Estimated standard error of the mean is the standard deviation of x, or this x, divided by the square root of n, where n is the number of people in your sample. This is the unbiased estimate of the population variance. So we're going to take the square root, and we're going to divide this variance by n, and this whole thing is under the radical. So these two things are the same quantity. So for a concrete example, let's suppose that the mean is 10. That's our null. The alternative is that the mean is not 10. standard deviation of our observed data is 5, and we have 200 people on which this is based. Okay, so then our estimated standard error of the mean is 5 over the square root of 200. So that's 5 over 14.14, and that's 0.35. If we collect the data and our sample mean is 11, then our z-test would be 11 x bar minus mu, which is 10, over the standard error, which is 35. And that gives us an obtained value of 2.83. And since we're looking at z and the alternative is not 10, then the magic 1.96 up or down from there is what we'd want to see, and 2.83 is larger than 1.96, so we would say that the result is significant. So that's doing the test in z. Typically, we're not going to do it in z. We're going to use t instead because it's good for any size sample, whereas you need big samples for z, and then people will argue about whether or not your sample is big enough. So you can stop all that arguing just by using the t-distribution. So we use t when the population variance is unknown, which is pretty much always the case, and when the sample size is small, less than 100, and that's the usual case. So, but you're going to be using some kind of statistical package, and they're going to always use t instead of z if you do that. You can think of t as a short, fat relative of the normal. So here we got the normal as the solid black line that goes like this. And with smaller degrees of freedom, it's shorter and broader. So the tails are extended. And, out here at 3 standard deviations, that basically there's nothing in the normal. There's still something going on here with small degrees of freedom. And you can see that as the degrees of freedom increase, the normal and the t look more and more alike. So as the degrees of freedom increase, then z and t converge, and that's why when we have big samples, we can just use z. Don't have to resort to t. Degrees of freedom. All right, so here you see the shape of the t-distribution depends on its degrees of freedom. And degrees of freedom are always a simple function of the sample size. So n minus 1 or n minus 2 or n minus 3, something like that. A simple function of the sample size. One way of explaining degrees of freedom is that if we know the total or the mean, and we know all but one score, that last score is not free to vary. So it's fixed by the other scores. So 4 plus 3 plus 2 plus x is 10, then x has to be 1. So there's 1 degree of freedom here, one thing that's left to vary. If we know the total or the, all right, so that's degrees of freedom. And we're going to need to know the degrees of freedom to find the critical value of t for any given test. For the single sample t-test, we're going to go back to the same problem, but now use t instead of z. We're going to compare the outcome. Instead of 1.96 with the z distribution, we'll have some other number with t, and where you need to be for that 97.5 is going to change. It's going to be farther out as the degrees of freedom become smaller. So with smaller numbers of people, you're going to have to push out farther to get a significant result. Okay, so as in the previous problem, we have the null is mu is 10, the alternative is not 10, and the standard deviation is 5 still, but now instead of 200 people, we have 25 people. So the estimated standard error is still standard deviation over the square root of n. That's 5 over the square root of 25. That's 1. So the standard error of the mean is now 1. If our observed mean is 11, just like it was before, then our difference in means is still 1, but now we're dividing it by 1 instead of 0.35, and our obtained value of t is 1. So if we want the t with alpha at 05 and 24 degrees of freedom, so here we're talking n minus 1 for our degrees of freedom, that critical value is 2.064. So that compares to a 1.96 with Z. And 1 is less than 2.064, and so the result is non-significant. It's what you would expect on the basis of chance. Notice that everything was the same in this scenario, except that we moved from Z to T, and we went from 200 down to 25 people. The confidence interval for the mean using a single sample T is the sample mean, x bar, plus or minus the critical value of T times the standard error of the mean. So here we have 11 plus or minus 2.064, which is the critical value of T with 24 degrees of freedom, times the standard error, which is 1 in this case. So the interval, the confidence interval, in this case it would be, because I picked 0.5 here, it's going to be the 95% confidence interval for the mean, would be 8.936 to 13.06. So about 9 to 13. And that, of course, contains 10, so we're going to have a non-significant result for our sample value of 11. Okay, so there's the single sample t-test. Here's some R code for the t-distribution. So Q for quantile, quantile for T, and here it says combine 0.25 and 975. So we want the bottom 2.5% and the top 2.5%. And now we tell it we want T distribution with 7 degrees of freedom. And R will come back and tell us the values are minus 2.36 to 2.36. So, you know, in the Z, it would be minus 1.96 and plus 1.96. So you can see that, you know, it was 2.06 about for 25 degrees of freedom, and now it's about 2.36. So as the degrees of freedom get small, the value to beat the critical value pushes out farther and farther from 0. Here's QT with 0.25 and 975, so same quantiles again. But now we have 1,000 degrees of freedom, and the results are minus 1.96 plus 1.96. So here you're getting what you get for Z, the unit normal, essentially. And so when you have a large sample, lots of degrees of freedom, Z and T turn out to be the same thing. Okay, probabilities of T, so P for probability, value of T of 2 and 7 degrees of freedom. That pushes us to 0.975 from the bottom on up to, you know, this is our 96% about. So for a p-value, you'd say 1 minus probability of T, 2 degrees of freedom is 7, and you get P is 0.4. Now that would be significant if you had a one-tailed test, because it's less than 0.5. But you need to be going up to 975 to get a two-tailed test, because you'd go 0.25 and 975. Okay, so there's some R code for T distribution. Take a minute. So I want you to explain how the distributions of Z and T are related. And I want you to look at this. 75 and not 75. So those are our null and alternatives. Standard deviation is 14. N is 49. T is critical value at 0.5 with 48 degrees of freedom. 49 people is 2.01. So, well, stop that. So construct a rejection region. Draw a picture to illustrate. So go ahead and do that. Where is your rejection region? Okay, so now that's the background for T. So now we're going to show you, well, actually that was the single sample for T. So now I'm going to show you the stuff you need to know for two samples for T. Most of the studies have at least 2 groups, so we got male versus female or experimental versus control, something like that. This is really the most common kind of t-test. We want to know if there's a difference in the population, and our best guess of the size of that difference is the difference in sample means. So Turns out that the difference in sample means, the expected value, which is the mean of the sampling distribution of this stuff, is unbiased. So it turns out the expected value of the mean of first group minus the mean of the second group is expected value of the first group minus the expected value of the second group. We know that the mean is an unbiased estimator of the population value. So we get mu1 here, and then this is the mean of the sample for the second, and that's the second mean. So we get an unbiased estimate of the difference in population values. The variance of the difference between the two means is the variance of y bar 1 minus y bar 2, and that thing turns out to be equal to the sum of two variances. This is the variance of the mean for the first group. This is the variance of the mean for the second group. So this is the squared standard error of the mean. Squared standard error of the mean. So the standard error of the difference is the square root of the variance of the first mean plus the variance of the second. So what this says is that, this mean is going to have some variability. If we do it over and over again, we find the mean over and over again. And the second mean, if we were to sample over and over again, would have a variance to it. And those are these two variances. And to find the standard error of the difference in means, we have to add those together and take the square root. In the single sample, only one varied, y1 varied, mu never changed, so there's no variance to that. So this is the idea in the difference between means, the standard error of the difference. Okay, so we're going to estimate the standard error of the difference because we won't know it. So we're going to estimate the variance of the first mean, we're going to estimate the variance of the second mean, and we'll take the root of that, and that will give us our estimated standard error. We could do a two-sample test with Z or T. For large samples, we're allowed to use Z, and since we've been studying Z, we're going to look at that. So this says the mean of the first minus the mean of the second, so I've switched from y bar to x bar. The variance of the difference in the two means, and now this is the difference in the two populations. So we can test whether this difference is very different from this difference, and we're going to divide through by the standard error of the difference in means. So how much do we expect these things to vary? It's typical to use the null hypothesis that the difference in means is zero. So we got your pain-free versus your aspirin, and we're looking at how well they control pain, and the null hypothesis is typically that the difference in the means is zero. There's no effect in the population. And it's conventional to assume that this difference is not zero for the alternative. So that'll give us, if we do that, a two-tailed test. Let's suppose that we have, for the first group, a mean is 10, and we have 100 people and standard deviation is 2. For the second group, we have a mean of 12. We have 100 people, standard deviation is 3. Then to actually carry this thing out, we need to know the standard error. So the standard error, well, the standard deviation is 2. Variance would be 2 squared or 4. Divide through by n, which is 100. Standard deviation is 3. Variance is 9. 3 squared. Divide through by 100. Then we add those two things together. 4 and 9 is 13. Divide by 100. That's 0.13. Take the square root. We get 0.36. So that's our estimated standard error of the difference in means. The value of z that we would get would be 10 minus 12. So it's a difference of 2 in our two means. And we're testing the null hypothesis that the difference is 0. So, that 2 is compared to 0. And if we do 2 minus 0, we're going to get 2. And we divide that through by 0.36. And that gives us a value of z of 5.56. Of course, that's quite large. That's a big big difference. Okay, so there's a two-sample test, but it's done in Z instead of T. The independent samples T, we're going to do the same kind of thing as we did for Z. So we're going to, the difference in the two means, and here I swap nomenclature on you again, X bar and Y bar doesn't matter. We're going to look at the difference between the two population values that we hypothesized. We're going to compare that to the standard error of the difference in means. So the difference in means and the standard error of the difference in means. There's a lot of statistics says, let's look at the value of the thing and compare it to its standard error. So this is the same kind of idea as Z. How big a difference is this compared to its standard error? So this is the standard error of this is the standard deviation of the statistic, the difference between means. All right. So in the independent samples T, our degrees of freedom will be number of people in group 1 minus 1 plus the number of people in group 2 minus 1, or our total number of people minus 2. So it's total n minus 2. Now we've got to subtract 2 from our degrees of freedom instead of 1. So you can think about this as we lose a degree of freedom each time we estimate a mean. So in the single sample, we only had to estimate one mean. Here we have to estimate two means. If the standard deviations are the same and the sample sizes are the same, then the standard error of the difference is variance of the first group, which is the same as the variance overall, divided by the number of people, and the variance in the second group, which is just the same thing, divided by the number of people here. So variance of the mean, and we can pull out the variance of the data and look at 1 over this plus 1 over that. So we're going to take the variance and we divide through by n if it were just one value, but here we're going to have n1 plus n2 for standard error of the difference. So here we're having to assume that the variance in both groups is the same, and there are varieties of the t-test that don't assume that, and you can use them. They're a little bit more conservative. But for the presentation, we're going to assume that they're the same. Okay, so the pooled variance, which we're assuming the variance is the same, and we got two different groups that we use to estimate that. The pooled variance will be number of people in group 1 minus 1 times the variance in 1 plus number of people in group 2 minus 1 times variance in group 2 over n1 plus n2 minus 2. So you just have here a weighted variance. So you're going to weight the variance by the degrees of freedom. Fisher decided to do it this way. You could use just the number of people if you wanted in each group, or if you just did the average, you could just take s squared 1 plus s squared 2 over 2, right? The idea here is that in the population there's one value, and both of your groups are being used to estimate that value. So the group with more people ought to have more weight because it's going to give you a more precise estimate of that variance. So the group that has the better estimate should get more weight. So that's what's going on here in the pooled variance estimate. We're taking a weighted average, and Fisher decided to weight by degrees of freedom instead of by the number of people. Very similar either way. You're going to get pretty much the same result. Okay, now the standard error is going to be related to the pooled standard, the pooled variance. So, the pooled variance here is the one on the top. The standard error, we've got to take this pooled variance, and now we've got to divide it by the sample size, essentially. Well, this thing here does that. So you remember when you had to multiply fractions, you've got to get the least common denominator and then that's essentially what's going on here. So we've got two different sample sizes, so we need to account for the two different sample sizes. And but the idea is the same as what we're doing here. We've got the pooled estimate of this variance, and now we're going to divide through by n1 and n2. These were the same here, and now they're different. So we're going to take the pooled variance, we're going to divide by n, we're going to take the square root, and that's going to give us our standard error of the difference. Okay, so here's our formula for the standard error of the difference. Here's our formula for t, and it looks just like z, except for I used x instead of y, but same thing. Now, our null is, again, the difference in means in the populations is 0. Alternative is not 0, so we have a two-tailed test. We got some sample data now. First group mean is 18. The variance in that group is 7, and there's 5 people in that group. I would advise you not to do a test where you've got this few people. I would say go get some more people before you do your test, but we're doing this for the sake of illustration. Second group, we have a mean of 20, we have a variance of 5.83, and we have 7 people. All right, so our estimated standard error of the difference, we're going to take 5 minus 1 is 4, so degrees of freedom here times the variance of 7. And then we got 7 minus 1 is 6 times 5.83. Then we're going to 5 plus 7 minus 2, so these are total degrees of freedom. And so then we got, so this is our pooled variance, and now we got to divide by n, and that's 5 and 7 is 12, and 5 times 7 is 35. So this is going to reduce this. So we carry out the addition, subtraction, multiplication, take the square root, and our estimated standard error is 1.47. So our t is going to be 18 minus 20 minus 0 over 1.47. That's minus 2 over 1.47. That's 1.36. And it's not significant because it's less than, it would have to be, minus 1.96 would be bigger than that. Turns out that with 10 degrees of freedom, it needs to be 2.23. Or in this case, it would be like less than minus 2.23. So it is not a significant difference in our example. So that's how you would actually compute the independent samples t by hand from the given. So you got two means, two variances, two sample sizes. You plug all that stuff in and you come out with a t-test. Okay, so I want you to take a minute and recall what the standard error of the difference between means is. What are the things that influence the sample size of the standard error of the difference between means? So what is that thing? How do you make it big or small? Describe a design where you tell us what the independent variable is, what the dependent variable is, that makes sense to use the independent samples t. So how much you actually employ this thing? Try to be realistic about it. Okay, so that's the independent samples t, and now the dependent samples t. So in the dependent t, you've got two groups, but the observations come in pairs. So you've got brother and sister, or you've got a repeated measure. So you've got each person is measured twice, so you've got two people that are related somehow. When you have dependency like that, then the variance of the difference is going to be the variance of the first mean plus the variance of the second mean. So that's what you had before. But now we're going to subtract 2 times the covariance of the first and second means. All right. So what this means is that if there's a good correspondence or good correlation between the two groups, that the standard error is going to be reduced from what it was in the independent groups. So here we've got the independent groups. We're going to subtract something from that. And that means that the standard error is going to go down. When we take the square root of this, we're going to have a smaller value in here, and when you take the square root, you're still going to have a smaller value. And that's pretty cool because now the yardstick for determining the size of the difference in means that you see, how close are those means? Well, that yardstick is going to shrink, and it's going to make the observed difference in means bigger, and it's going to be easier to find a significant difference. So what we actually do typically in practice is to, instead of figuring this, which you can do, instead we find the difference between the pairs. So call score D, which is first group, first person and second group. So subtract the scores in the paired observations and call them differences. So the average difference is the sum of the differences divided by the number you got. The variance of the differences is take each difference, subtract the mean, square it, add them up, divide by n minus 1. So this is just your standard variance. Your estimated standard error of the means for the differences is the standard deviation of these, as I take the square root, and divide by the number of pairs. Okay, so n is no longer the number of people, it's the number of pairs. And then t will be d bar, so what's your mean, and then your expected value here, so this would be mu, whatever you think it's the hypothesis is, and you divide through by your estimated standard error. Degrees of freedom is the number of pairs minus 1. So this is the same, it doesn't look exactly like it, but this is really the same formula as what we did for our single sample t. All right, so here's an example with a whopping 3 observations. We're looking at brothers and sisters scores on figure skating as assigned by a panel of judges. And you see the brothers, we got 1 brother-sister pair, we got 2 brother-sister, we got 3 brother-sister pairs. The mean of the brothers is 5, the mean of the sisters is 6. And now we're not going to analyze these. What we're going to do is we're going to compute a difference. So sister minus brother is 2, 1, and 0. So these are our differences. The mean of the differences is 1. The variance, so we're going to take d minus d bar and square that. So 2 minus 1 squared is 1. 1 minus 1 squared is 0. 0 minus 1 squared is 1. And so there's our differences. The standard deviation of that is sum of d minus d bar squared over n minus 1. That's 1. And our estimated standard error is 1 over the square root of 3, because n is 3 in this case. That's 0.58. So we've got a mean of 1 minus 0, because our hypothesis would be, the null would be that there's no difference between brothers and sisters. So it's 1 over 0.58, that's 1.72. And we're going to, you compare that to t distribution with 2 degrees of freedom, and it's not going to be significant. Okay. All right. So I showed you the single sample t. I showed you independent samples t. I showed you dependent samples t. They're, sort of bread and butter. This is the entrance to inferential statistics, is the t-test. T is based on assumptions of normality and homogeneity of variance. So you can test for both of these. And you remember normality, you're going to look for QQ plot, and the normality assumption is the normality of the dependent variable within groups. So there's no assumption that the dependent variable, when you combine all the data, is normal. The assumption is that it's normal inside each of the groups. And homogeneity of variance means that the variance is the same in each of the cells. We assume that because we assume there's one population, and each of our cells, or each of our groups, is used to estimate that one population variance. You can test for the homogeneity of variance with that homogeneity of variance test. And we did that in, we're talking about F. As long as the samples in each group are large and nearly equal, t-test is robust, even though the assumptions are not met. So, inferences about means, we got the central limit theorem there. So the t-test is going to work pretty well as long as you've got big samples and more or less equal numbers in each group. if you don't have equal numbers in each group, you could have really different variances, and you could get into trouble. So, most of the stuff that we do, if you're doing an experiment or you're assigning people to groups, chances are good you're going to have a reasonable number of people and reasonable balance of numbers in each group. If you have really small numbers of people like this, then you may not even get around to doing parametric statistics. But this is just an example. Use more people. All right. All right, review. Describe a design where it makes sense to use a single sample t. Describe a design where it makes sense to use a dependent samples t. So you already did the example where you created a study for the independent samples t. Now we want single and dependent. So come up with some good concrete illustrations of these things.